Bismillahirrahmanirrahim. Welcome back to Mathematical Methods of Physics. Today we will go through lecture number 9 of this course. In lecture number 8 we studied Fredholm integral equations, the existence and uniqueness of the solutions of Fredholm integral equations by using Fredholm alternative. Basically we studied a couple of propositions over there which tells you about the existence and uniqueness of the solutions, and then we did 3-4 examples as well where we have seen example where there were no solutions at all, and there were infinite many solutions, and there were unique solutions as well. Basically, when you had those eigenvalues and eigenfunctions thing, if your lambda, which is coming in the Fredholm equation, if that is equal to the eigenvalue, then your fx has to be orthogonal to your eigenfunctions to have a solution. If it is not orthogonal, you won't have any solution. And if your function is orthogonal to the eigenfunctions, then you will have infinite many solutions. So to get a unique solution, your lambda should not be equal to the eigenvalue. In that case, you will have a unique solution of the non-homogeneous Fredholm integral equation. So I think in last 2-3 lectures we studied this Fredholm alternatives, and we saw different examples, and we solved those examples through different procedures as well. So today we will be starting a new topic which is called Green's function. So outlines for today is Green's function, and to study Green's function it's important to study properties of Dirac delta function. Dirac delta function is basically a function which is also called impulse function as well, which blows up at one point and it's zero elsewhere. So I hope you have studied differential equations before, so you must have seen this function and you know the properties of this function already. But if you haven't, you don't have to worry about that. We will be doing it thoroughly, so don't worry. If you don't know about Dirac delta function, it's okay. I will be going through it very thoroughly, and you will I hope you will understand what this function is. And then we will go on and develop a Green's function in one dimension. Alright, Green's function has very huge applications in study of differential and integral equations. So basically it's a very important topic. You can solve many differential equations with the help of Green's function, and you can solve even integral equation with the help of Green's function as well. So let's start with the properties of Dirac delta function. This will be our first topic of today's lecture, properties of Dirac delta function. So first of all, what is the definition of Dirac delta function? It's a delta x, small delta, right? Small delta of x. It is 0 if x is not equal to 0, and it is infinity when x is equal to 0. So basically it's impulse function. At 0 it gives you impulse, infinity. It's 0 everywhere. All of a sudden it goes to infinity, and then it's again 0. So it gives you impulse, very quick impulse. It blows up at x equal to 0. Or if you want to write this is about 0 at x equal, you can define Dirac delta function somewhere else as well. Let's say you don't want impulse at 0, you want impulse at a. Then you can define Dirac delta function as delta of x minus a. X minus a will be 0 if x is not equal to a, and it will be infinity if x is equal to a. So it gives you impulse at x is equal to a. Alright, so you can define these two functions. This is the special case of this one. If I take a to be equal to 0, then I have this function. Alright, so the properties, this is the definition basically. What is the property? Property is that area under this Dirac delta function is always 1. Even though it goes to infinity at one point, but if you calculate the area from minus infinity to infinity delta x, it gives you 1. Alright, or if you integrate from if you integrate this one, delta x minus a, it will still gives you 1. Alright, so it doesn't matter where the origin of this function is, at 0 or at a, the area under this curve is always 1. And this is from minus infinity, of course. It's again a typing mistake. It's a minus infinity to infinity, delta x minus a to 1. It's a even function. Even means when you take minus out here, you see delta of minus of x minus a, it gives you delta x minus a again. So this is an even function. X minus a or a minus x, there is no difference. Alright, so this is another property. Delta x is the derivative of this heavy side function. I hope you have seen Heaviside function. If not, then it is a step function, it's nothing else. Heaviside function is defined by this, that if x is greater than 0, it's 1, and if x is less than 0, it's 0. So on the right of 0, it's 1, on the left, it's 0. So it's a one-step function. 0 and again 1. So it's a step function, only one step over there. So this is a Heaviside function. So derivative of the Heaviside function is basically Dirac delta function. This is a very nice property. If you multiply your Dirac delta function with any function f of x and integrate it, what it does is it picks up the value of f at x equal to a. You see, nothing else. It picks up the value of f at x is equal to a, and delta is gone. All right. So this is f of a. It's a very nice property of Dirac delta function. Similarly here, fx delta x minus a is the same as fa delta x minus a. Can you see the reason here? The reason is Dirac delta function only defined at x is equal to 0. Otherwise it's 0. If x is not equal to a, it's 0. So on the left hand side, if x is not equal to a, it's 0. So only contribution you are getting is at x equal to a. So you can multiply by fa, it will give you the same thing. Because at x equal to a, the function value is f of a. So f of a multiplied by delta or fx multiplied by delta gives you the same thing. If you multiply your delta function with x, it gives you 0. And also, you can define another function, delta n of x, which is n over pi e to the power minus n x squared. It's kind of Gaussian function, you see. It's kind of a Gaussian function, isn't it? E to the negative n x squared. If you have seen the Gaussian function, normal distribution in statistics, right? It's a Gaussian function, and if you define this to be a delta n, then the limit of this function is your delta function. If you take the limit of this function, it gives you a delta function. So see, the limit as n goes to infinity of this function gives you delta x. So Gaussian functions approach this Dirac delta function eventually. So these are basically properties of Dirac delta function. Let me again explain it a little bit. It is 0 if x is not equal to 0. It's infinity if x is equal to 0. So basically this is this kind of function. All right. This goes to infinity here. This is the, so it's 0 everywhere. It's 0. All of a sudden it goes to infinity, right? And then it's again 0. All right. Again it's 0. So it goes to infinity at x equal to 0 over there. All right. So this is basically y, but it goes to infinity. This is at 0, it gives you an impulse. If you want to define at x equal to a, you can do that. Let's say this is your a. Then it gives you 0 before a, and it gives you 0 after a. But at x equal to a, it goes to infinity. So this is your delta function at x minus a. So it's your choice if you want to keep this a at 0 or somewhere else. Heaviside function is this. This is y, this is x. So Heaviside function is 0 before 0 and 1 after 0. This is your Heaviside function. All right? This is your Heaviside function. Before 0 it's 0, after 0 it's 1. And if you take the derivative, of course, derivative of 0 is 0, derivative of 1 is 0. So it will come down. It will become almost, but at 0, your derivative is not defined. It's infinity. So that's why at 0, it gives you nothing. So that's why the derivative of Heaviside function is the Dirac delta function. Gaussian function, which I wrote at the end, let me define that as well. N by pi e to the minus n x squared. So you see, by changing n, you are changing this multiple here. So these are all Gaussian functions. Gaussian functions look like this, right? These are the Gaussian functions. So if you increase n, what will happen? The width increases like this. It goes like this, right? Increase, and again, you will get like this, right? It will be very long and it will be narrowed like this. So eventually it is going inside from here, but it's going up, up, up from here. So what will happen when n goes to infinity? You will have almost 0 here, and again a pulse, and then again 0, right? So basically your Gaussian will almost look like this when n goes to infinity, like this, right? So this goes to infinity, it's not stopping anywhere. So that's why as n goes to infinity, your delta nx approaches delta x. All right? So this is the reason. So these are little explanations which we of the properties. The property of being, if you want to prove it, why this delta x is equal to 1, all right? So see the Gaussian, if you remember, area under the normal curve is always 1. So if you integrate delta nx dx, this is 1 because it's a Gaussian. Area is almost always 1. So if you take n goes to infinity on both sides, this will become delta x and 1 will remain 1. So area under the delta x is also 1. All right. So these are very nice properties of the Dirac delta function. We will be using them in Green's function, in the development of Green's function. That's why we studied these properties. All right. So these are the properties, and I have explained a little bit about these properties in writing. So let's move on and study the development of Green's function in one dimension. You can develop these Green's function in higher dimensions as well, but we won't need it here, so I will restrict myself to only one dimension. Maybe in higher courses you may study Green's function in more than one dimensions. Idea is almost the same. All right. So if you understand Green's function in one dimension, of course you can do it in 2 or 3 dimensions as well. So let's start the development of Green's function in one dimension. What are basically Green's function? The Green's function method is one of the most important methods which helps in finding the solution of non-homogeneous ordinary or partial differential equations. We are especially interested in using Green's function to show how a boundary value problem is reduced to a Fredholm integral equation with kernel is equal to the Green's function. So we will study Green's function independently, and then we will relate these Green's function to the Fredholm integral equation where your kernel is Green's function. So you can treat your Green's function as a kernel in the study of the integral equations. All right? So these will be our main aim. In the following, we illustrate a simple practical problem from mechanics whose solution can be composed of a Green's function named after the English mathematical physicist George Green, 1793 to 1841. So he was an English mathematical physicist basically who introduced Green's function, so that the name Green's function is after his name basically. He was George Green. So let's see that practical problem from mechanics, which will lead us to Green's function. There are many other proofs as well. You can see a Green's function in many other applications, many other formulations as well. But this is one of them. So I thought you may be interested, or it will be interested to know how from mechanics, a problem from mechanics can help us guide through this Green's function. So a distributed load of a string. All right. So we'll consider a string with a load which is distributed along the string. If you have studied mechanics, of course, this will be easier for you guys. Assume an elastic string stretched to a length L under tension T. Let the string bears the distributed load per unit length Wx, including the weight of the string. So what we have here is, you have a stretched string of length L, and of course there is a tension now in the string, we call it T, and now there is a distributed load. Load is not on one point or somewhere on the string, it's distributed along the string. All right, so that's why it's stretched like this. All right, and weight Wx is basically the unit length, weight per unit length. All right, because it's distributed, so everywhere it's equal weight. Since the deflected string is in equilibrium, the net horizontal and vertical forces must be 0. Alright, so because there is a weight on the string, alright, so now it's stretched down a little bit, so now it's in equilibrium. If it is in equilibrium, then horizontal and vertical components of the forces, they cancel the effects of each other. So sum of horizontal forces must be equal to 0, sum of vertical forces must be equal to 0. So let's take a small element of the string from x to x plus delta x. Delta x is a small incremental length of the string. So if you pick these two up, these two dots, so I zoomed in and see this is your from x to, this is a stretched string with weight, alright. So we are defining horizontal angles here. At this point x, your horizontal angle with the force is alpha 1 because tension, you see there is a force applying, tension force, alright. So if this is the force, if this is the direction of the force, and let this force make an angle of alpha 2 with the x-axis, and F1 makes an angle of alpha 1 with the x-axis, and Wx is of course the weight goes downwards. Alright, so this is the picture. This is basically what's happening with the small element of the string. Right, small element of the string. That's what happening. That is what is happening with this small element of the string. Now, if you recall, what is the, if this is F2 or if this is F1, what are the horizontal and vertical components of force? F1 cosine alpha and F1 sine alpha, right? If F1 is making alpha angle with the x-axis, then F cosine alpha gives you the horizontal component and F sine alpha gives you the vertical component. So here I am getting F1 cosine alpha 1, and here it's F2 cosine alpha 2. These two are horizontal forces. Alright, and vertical forces are F1 sine alpha 1, F2 sine alpha 2. So you have to equate them because we just mentioned, alright, so horizontal and vertical forces must be equal to 0. That's why F1 cosine alpha 1 should be equal to F2 cosine alpha 2. This should be equal to the tension of the string. F2 sine alpha 2 should be equal to F1 sine alpha 1 minus Wx delta x. Why? Because you see, this is also a vertical force, Wx delta x. Alright, this is downwards. So that's why it's being added to F1 sine alpha 1. Here the positive direction of Wx has been chosen upward. We consider the deflection to be so small that the forces F1, F2 will not differ much from the tension of the string. The deflection of the string is very, very small. Alright, this deflection is not very big, very small deflection. Like this is the string and a little deflection like this. It's a very small deflection. So the forces F1 and F2 are basically can be approximated by the tension forces basically. Alright, if your deflection is not small, you cannot do that. You cannot say that your forces will be the same as the string tension T. Alright, if the deflection is very, very small, then you can say that these forces can be approximated by the tension force. Alright, so tension is equal to F1 is equal to F2, so we obtain approximately T sine alpha 2 is equal to T sine alpha 1 minus Wx delta x. So this is what you got. I replaced F1 F2 by T. Alright, we know that for small alpha, we can replace sine alpha with tan alpha. If alpha is very, very small, we can replace sine alpha with tangent alpha. Therefore, above equation can be written in the form, we replace the sine alpha 2 by tangent alpha 2, sine alpha 1 with tangent alpha 1. Alright, but we also know that if alpha 1 is the inclination angle, then tangent is the slope. Right? Tangent of the inclination is the slope of the curve. Alright, and slope is given by dy by dx. Slope is dy by dx. So tangent alpha 2 is dy by dx at x plus delta x, and tangent alpha 1 is dy by dx at x. You see here, this is tangent alpha 1 gives you the slope at this point, alpha at x, and tangent alpha 2 gives you the slope at this point, which is x plus delta x. Alright, so that's why the derivatives at x and x plus delta x. So it means you can replace this tangent alpha 1 by the derivative and tangent alpha by tangent alpha 2 with this derivative. So if you replace, you will get this one. All right, tangent alpha 2, tangent alpha 1. So we replace them by the derivative, and here if you bring it to the left and divide by delta x, you will get this one, right? See, I brought it to the left, so it's a minus sign, and this delta x is divided here on the left, so there is no delta x remaining on the right hand side. And now if you take the limit as delta x goes to 0, delta x was a small element, so we want to see what is happening at the point x, right? We want to see what is happening at this point x. So what we will do is we will take the limit as delta x go to 0, and this will give you the motion of the string at x. All right, so if you take this limit, what is this? Function at x plus delta x minus the same function at x divided by the delta x gives you the derivative of the function. The function is itself first derivative, so the derivative of the first derivative gives you the second derivative. So this is the second derivative of y with respect to x is equal to minus wx by t. If you multiply t on the left hand side, this is what you get. So this is the differential equation satisfied by the deflection curve of the string. So this is the differential equation, this is the motion, that how much the deflection of the string will satisfy this equation at any point x. So let me explain how we got those approximations. We said sine theta is approximately equal to tangent theta if theta is small. Right? So basically tangent theta is equal to sine theta over cosine theta, right? So if theta is small, very small, then cosine theta is approximately equal to 1. Because what is cosine 0? Cosine 0 is 1. So if theta is very, very small, close to 0, then cosine theta will be very, very close to 1. All right? See, cosine theta is this. Cosine starts from 1, it goes to 0 like this, right? So if this theta is very, very close to 0, your cosine theta will be very, very close to this 1. All right? So it means this thing is approximately equal to sine theta divided by 1, right, which is sine theta. So that's why we took the approximation that for small theta, this is approximately equal to sine theta. All right, so this was our first approximation. The second one was if you have a curve that whose tangent makes an angle theta with the x-axis, then the slope of curve will be equal to tangent theta. All right, but the slope is also equal to, if this is your y function of x, all right, then slope is also equal to dy by dx. All right, so that's why we replaced at the end tangent theta by dy by dx. And now it depends on theta. When we took theta alpha 1, we replaced it at x is equal to x. The reason is alpha 1 was the angle at x, right? Here, alpha 1 was the angle at x, and alpha 2 was the angle at x plus delta x. So that's why dy by dx at x plus delta x gives you tangent alpha 2. All right, and here dy by dx at x gives you tangent alpha 1. All right, so these are the two things we used later on in our modeling. All right, so one was this approximation, and the second was how we got this tangent replaced. All right, at the end we use this definition: f of x plus delta x minus f of x divided by delta x in the limit delta x goes to 0 gives you the derivative of x. Right? So what we were having was, we had dy by dx at x plus delta x, we had dy by dx at x over delta x. We had this thing. So our function is, and we took the limit as delta x goes to 0. So this is the derivative of, this is our function, right? This is our function dy by dx, and we took the derivative of that at x, right? So this gives you second derivative dy by dx square at x. So generally we don't write this at x. It's understood that the value has to be at x. So that's why we only wrote d2y by dx square. Right? When there is no at x means it is understood that the value is at x. All right. So these are the little explanations which we were using, which we have used in our derivation. All right, so this is what we got at the end, which gives you the motion of the deflection of the string. Now let's move on and see another problem from the mechanics, which is a concentrated load of a string. Instead of the distributed load, let's consider the concentrated load on the string. Definition: a concentrated load is a mathematical fiction which can't be realized physically. Any non-zero load concentrated at a single point implies an infinite pressure which may break the string, is known as concentrated load. All right, so we are basically applying a load, a non-zero load on a single point of the string. All right, and it creates infinite pressure so that it will break the string eventually. All right, it may not happen physically, right? But we assume that the concentrated load eventually produces infinite pressure on the string. All right. So if we consider a concentrated load rather than a distributed load, what will happen to our study of the string, deflection of the string? In the absence of distributed load, we have Wx equal to 0 because Wx was a distributed load. There is no distributed load, so Wx is 0. The colored equation here in the last derivation, this will take the form t d2y by dx square equal to 0. Because we said Wx is not there, so right hand side should be equal to 0. So this is what we got. For all points of the string. Alright, this implies that y is a linear function. Do you see that why this y is a linear function? Because second derivative is 0, so if you integrate it twice, you will get c1x plus e2. It's a linear function. So the first derivative will be constant, second derivative constant time x plus another constant. So it's a linear function. Y is a linear function. Any linear function has second derivative equal to 0. So this is basically the picture, what's going on. We are taking the concentrated load on one point. So this is the one point. Now tension F1 is going this way, F2 is going this way. All right. So let's say this F2 makes an angle alpha 2, F1 makes an angle alpha 1. All right. The deflection is this y of x. T is the tension in the string, of course. And now in this case, tension and F1, F2 have the same direction. All right. So let's say this point is eta, somewhere between eta. So this will be L minus eta. You see, from here to here it's eta. This is L minus eta. Now, if you resolve the forces acting on the string, then of course F2 cosine alpha, which is the horizontal force here, and F1 cosine alpha, which is the horizontal force here. Because alpha 2 is the angle which F2 makes with the x-axis. So this will be F2 cosine alpha 2. This will be F1 cosine alpha 1. So these two will balance each other. Horizontal forces will balance. Similarly, the vertical forces. Vertical forces are F1 sine alpha 1 and F2 sine alpha 2. These are the vertical forces, should be equal to negative R. This R is the force which is acting down. See, it's a concentrated force, concentrated load. So on one point, of course, there is a weight, right? There is a force acting on that one point. All right. So let's call that R, right? So vertical forces should balance this force R. All right. When the deflection is small, we can assume that F2 cos alpha 2 is equal to F1 cos alpha 1 is equal to T, or simply F1 F2 is equal to T. When the deflection is very, very small, then your F1 F2 can be approximated by T. If the deflection is small, what will happen? If deflection is very small, cosine alpha 2 and cosine alpha 1 will be equal to 1. I just explained that in the handwritten slide, that if theta is very, very small, cosine theta can be approximated by 1. So if cosine alpha 1 and cosine alpha 2 can be approximated by 1, so f1 and f2 should be equal to your tension if deflection is very, very small. All right, and the other, this one will become f1 sine alpha 1 plus f2 sine alpha 2 is equal to negative r. All right, this will take this form because I just said that f1 and f2 are capital T, so I divided that T on the right hand side, and sine alpha 1, sine alpha 2 are again, they will become tangent alpha 1 plus tangent alpha 2, right? I showed you before that cosine alpha can be taken to 1, so tangent alpha will approximate sine alpha, or sine alpha will be approximated by tangent alpha. So tangent alpha, sine alpha 1 and sine alpha 2 are replaced by tangent alpha 1, tangent alpha 2. So this is negative r by t. Now what is tangent alpha 1? It's, now see, it's a straight line, it's not a curve, it's a straight line. All right, let's call this length, this deflection, to be equal to beta, and from here it's eta. What is tangent? Tangent is perpendicular over base, perpendicular over base. So beta over eta, beta over eta. And because this perpendicular is going down, that's why we are having minus beta here, because it's downwards. Positive direction of y is upwards. So if beta is the length downwards, so basically it's negative beta by eta. And similarly, what will be alpha 2? Now perpendicular is the same, which is negative beta, and this length is L minus eta. So perpendicular over base. So beta over L minus eta, again with a negative sign. All right. So instead of getting the derivatives here, we got simple numbers, beta and eta. The reason is we are having straight lines instead of curve. When we have curve, we get derivatives, because slope of a curve is always a derivative of the function with respect to x, because it's changing every time. Slope of a straight line can be approximated by a constant. All right, vertical displacement divided by the horizontal displacement, that is the slope. Run over rise, rise by run, that's what we call rise by run, right? Rise divided by run. You are running this way and you are rising as well. So the rise divided by run gives you the slope of the straight line. All right, so this is what you got. After simplification, this is what your beta is. This implies beta is given by, if you solve this thing for beta, this is what you get, r times 1 minus eta, eta by t. So r times L minus eta by t, L eta. This is small l, that's why it looks like I, but it's L. Where beta is the transverse deflection of the string at x is equal to eta. Of course, what is this beta? Beta is the deflection at this point eta. This is the point eta. At this point eta, this is the deflection of the string. All right. With the deflection beta known, it is a simple matter to use the similar triangles to find the deflection of the string at any point x. Now if beta is known to you, you can find the deflection at any other point x. All right. The results are, if you are here, somewhere here, if your x is between 0 and eta, if your x is between 0 and eta, if your x is between 0 and eta, you can find this you can find this deflection by using the similar triangles. Similar triangle means y divided by x should be equal to beta divided by eta, because they are similar. This alpha 2 is the same for these two triangles. This small triangle and this big triangle, these are similar triangles. In similar triangles, corresponding ratios are equal. Y by x and beta by eta has to be same. All right, so y by x equal to beta by eta. These are the same. So this implies that yx is equal to what is beta? Beta is this. So replace this beta, multiply by x. This is your yx. And if you are on the right hand side here, if your x is between eta and L, then of course we can use these similar triangles. Then your y by x will be equal to beta over L minus eta. Y over L minus x, beta L minus eta. So this is what you get. Y over L minus x should be beta over L minus eta. So this will be your yx. All right. So all you are getting is, see, you are getting x here, and in this case you are getting eta here. Here eta is inside, x is outside, here x is inside, eta is outside. All right, so let me explain you a bit on an empty slide. This was your string, right? Let's call this beta, right? This length is beta. This is your eta point. So if your x is between 0 and eta, right, let's say somewhere here, this is your x and this is your deflection y. So see, this angle is the same for both the triangle. This triangle, if I take this as alpha 1, then tangent alpha 1 from small triangle is y by x. And if I consider the big triangle, this one, angle is still the same, tangent alpha, this will come from beta divided by eta. All right, this is your x and this whole length is eta. So this is beta over eta. So this is your first case. Y by x is equal to beta by eta x. Now the value of beta is known to you. You replace it here, you get y of x. All right, this x is gone. All right, so that's how you got yx between 0 and eta. Now if you are here on the right hand side, let's say your x is here now. If this is x and this is y of x, right, then this is the common angle alpha 2. So tangent alpha 2 from this smaller triangle gives you y divided by this length. And this length is L minus x, because total length is L. X is from here, from 0 to x. This is your x. So the remaining is L minus x. And same thing from the bigger triangle gives you beta over L minus x. All right. So from similar triangles you got y. So y is beta over L minus x times L minus x. Sorry, this is eta. This is eta. So again, the value of beta is given. You replace the value of beta, you will get y for 0 to eta as well. All right. So that's how you got two values of y in the interval 0 to eta and from eta to x. All right. So that's how we got these values of yx in two different intervals. Let's put it together. Thus the results are yx eta. Now y is not depending on just x. You see, in both these equations, you see y depends on eta and x. Y depends on eta and x. So basically y depends on x and eta. This is r L minus eta x and this is r L minus x eta. All right, and this is the case when x is between 0 and eta, and this is the case when x is between eta and L. Here yx eta is used rather than yx to indicate that the deflection of y depends on the point eta where the concentrated load is applied and the point x where the deflection is observed. All right, so your y depends on both the points, on this x where we are observing the deflection and on this point eta where the concentrated load is attached. So it depends on both the points, at the current point x and at the concentrated load point eta. All right, so it depends on both the points eta. These 2 points are respectively called the source point and the field point. All right, so x is called the source point and eta is called the field point. I guess eta is called the field point, source point, because the source of the deflection is eta. Because you placed a concentrated load on eta. This was the source of deflection. If you haven't placed any load on the string, it will not cause any deflection at all. So source of the deflection is eta, and x is basically the field point where you are observing the deflection now. That is a field point. Note that when r is a unit load, it is customary to use the notation gx eta. When you look at the literatures, when they replace this r by 1, let's say r is the load, so let's call it unit load because we just want to study the concentrated load. So it doesn't matter how much the load is. So it doesn't matter how much the load is. What you need to do is you just have to put some load. So just call it a unit load, 1 kg, 1 ton, whatever. Just make it unit, keep it unit load. So in that case, when r is replaced by 1, it is customary to use the notation gx eta instead of y, right? This is known as Green's function corresponding to the function yx eta. All right, so this is called Green's function corresponding to y. Thus, for the said problem, the given problem, the Green's function is given by L minus eta x by TL and L minus x eta by TL. All right. Many authors call Green's function as influence function as well, because this gives you the influence of the force on the string. All right. So your diffraction is caused by the influence of this Green's function. That's what you can call. That's the reason many authors call it influence function instead of Green's function. The Green's function is symmetric, and to keep it more simple, you can take this tension to be 1 as well. Tension is a string. You can take the unit tension on the string as well. If you do that, you can make it more simpler. L minus eta x by L and L minus x eta by L. All right. Green's function is symmetric. If you replace x and eta, you get gx eta back, right? So gx eta and g eta x are the same. These are the symmetric functions. So remark, with Green's function gx eta, an expression of deflection of a string under an arbitrary distributed load can be found without solving this equation. See, we haven't solved, this is the solution of the concentrated load. We did not solve this equation, this blue equation, which was the deflection of a distributed load caused by the distributed load on the string. So what we do is we can use that Green's function of the concentrated load to get the solution of this equation. And how can we do that? Let's see it from here. We divide the interval 0 to L into n subintervals by the points eta naught is equal to 0, eta 1, eta 2 up to eta n, and eta n is L. So we have partitioned our interval. From 0 to L, we have subdivided. We started from eta 0, eta 1, eta 2, so on up to eta n. First will coincide with 0, last will coincide with L. Such that your difference of any two consecutive etas, eta I plus 1 minus eta I, is equal to delta eta I. Let xi be any point from this interval, be an arbitrary point. Let us also consider that the position of a distributed load acting on the subintervals, namely w eta I, delta eta I. This is concentrated at the point xi I. The deflection produced at the point x by the load is the product of the load and the deflection produced at x by a unit load at the point x is equal to xi. All right, which is this one. So let me explain it separately how these things are working. So what we basically did is we said, okay, this is our string, right? This is our string from 0 to L. All right, so the what we did is we subdivided. We called this eta naught, this eta 1, this eta 2, so on, eta n minus 1, and this is eta n. So in general, any subinterval here is basically eta I minus 1 and eta I. So the length of this interval is delta eta I. All right? Delta eta I. Now what we are doing is we are saying that we have imposed a distributed load, so our string look like this. Instead of that, we subdivided it. We subdivided the string. All right, we subdivided the string like this. So at each point, I took the value at each interval. I said xi I is a point in this interval, eta I minus 1 to eta I, right? So xi I is any point in this interval. So I said instead of distributed load, what I can say is that that load which is not constant, which is distributed, so let's say that is a concentrated load at each point here, at each of these points. Distributed load means at each point there is some weight on the string. So we are saying that I can replace the load on this small element of the string by the concentrated load on one point xi I. So in this interval, your concentrated load is at xi I, which is delta eta I, and we know that that concentrated load should come from here, xi I, right? Because this gives you the concentrated load, right? So what I'm saying is the distributed load on the small interval can be approximated by the concentrated load at one point of that interval, because the interval is so small that the distributed load is almost the same as the concentrated load, and we can do this thing in each interval. So in each interval we have approximated the distributed load by the concentrated load. All right, so that's how we got. And now if we sum them up, so the total distributed load will be the sum of this thing on each interval. This will be sum on each interval. All right, so this will be the case. So if you sum them up on all the intervals, this gives you the total distributed load, all right, by using the concentrated load on each interval. So that's how we got this expression over here. You see, W xi I, delta eta I, Gx xi I. All right, so we sum it up over all the values of I. So adding all the deflection produced at a point x by the various concentrated forces, which together approximate the actual distributed load. So we can approximate our distributed load, actual distributed load, by these n concentrated loads. All right, so because n is big number, delta eta is very small, so that's why at each small element of the string we can approximate the distributed load by the concentrated load. All right, so this sum becomes integral when the limit delta eta goes to 0, because still we have to distribute it evenly throughout the string. So even if the increment delta eta is very, very small, this will not be enough. We have to take the limit as delta eta goes to 0, so that at every point we are having a concentrated load, at every point. So in the limit as delta eta goes to 0, this whole thing will become the integral. All right, because this is the Riemann sum basically, and the limit of the Riemann sum becomes the definite integration. All right, so delta eta will become d eta. So you got w eta, gx eta, and d eta from 0 to L. We have integrated throughout the interval 0 to L. And on the left hand side it's yx. What is yx? It's a distributed load. It's a deflection. So deflection will be given by this equation. So here, once the function is known, if your gx eta is known to you, the deflection of the string under any piecewise continuous distributed load can be determined at once by the integral equation. So if gx eta is known, and of course w eta is the distributed load that will also be given to us, we can find yx. All right, so to prove that this actually gives you the solution of that equation, let me go back. This equation. We said we haven't solved this equation. All right. So what if we can solve this equation? We approximated the solution of this equation by the concentrated loads, and we got this thing. So this is our claim that this is the solution of our second order differential equation, which was obtained from distributed load. So let's prove it. If this equation, if this integral equation is the solution of this equation which we got from the distributed load, then it must satisfy it. If I replace yx here, this should give me minus wx. So let's do it. T d2y by dx square is equal to 0 to L. I just replaced y by this expression here, right? Because the derivative is with respect to x and integral is with respect to eta, so I can bring, and also the limits are constant, so I can bring this derivative inside. So if you take the double derivative of this Green's function, all right, so this is only true if the derivative is equal to the delta function. Reason is, if you recall the properties of the delta function, we said if we multiply w eta with the delta function, it picks up the value of w at x, at eta is equal to x. All right, so it means that we should have something like this. This is our property of delta function. It means if I multiply w eta by delta x minus eta, what it will do is it will pick the value of w at x, this value x. So I will get minus wx. Because the right hand side is minus wx, it means this expression, this d2 of tg by dx square should be equal to minus delta x minus eta. This is the only way I will get minus wx on the right hand side. Alright? Where delta is a Dirac delta function. So from here we are getting this equation. Alright, so from here we are getting this equation. It means your Green's function gx eta should satisfy this differential equation, this non-homogeneous differential equation, that the second derivative of g with respect to x square should be equal to minus of Dirac delta function. This is the definition of g. Alright, so let's prove it here. Y of x is equal to 0 to L w eta gx eta d eta. This is what we are having. Let's call this equation 1, right? And we need to prove that this is a solution. 1 satisfies d2y by dx square t times equal to minus wx, right? So this is, let's call it equation number 2. So we need to satisfy this one. So first of all, I need to differentiate this once. Alright, so differentiating 1 with respect to x, we obtain dy by dx equal to, on the right hand side, d by dx from 0 to L w eta gx eta d eta, right? Let's call it 3. We know that in this case our gx eta is known. We know that gx eta is L minus eta x by TL. This is when x is between 0 and eta, and L minus x eta by TL when eta is when x is between eta and L. Alright, so we already know that. So by using this one we can differentiate also gx eta is the same as g eta x, right? So we use to differentiate, we use g eta x because we are, since we are differentiating with respect to, so we use g eta x because we are differentiating with respect to x. So if I do that now, if I write g eta x, all I need is replace L and eta, L minus x eta by TL. So it means now eta is between 0 and x because I replaced eta and x. So this is L minus eta x by TL, and your x is between less than L and less than eta. So now if you differentiate, first of all replace, therefore equation 3 becomes, right, it was equation 3, this equation. So I can break it from 0 to x and x to L because you see eta is there. Eta is there, so eta goes from 0 to L. So I have to break eta. That's why I have to do g eta x instead of x eta, because here I need the limits of eta from 0 to x and x to L, because we are integrating with respect to eta. So equation 3 becomes dy by dx is equal to d by dx of, you see I need to replace because I have w eta, gx eta, let me not write it here, it's d eta. So eta goes from 0 to x plus eta goes from x to L. Alright, so to bring in the last here I have values of x. X goes from 0 to eta and eta to L. But here our variable integration variable is eta. तो ईटा को हमने ब्रेक करना है 0 से x और x से l तक, इसलिए हमने रिप्लेस कर दिया x ईटा को ईटा x से, क्योंकि ये सिमेट्रिक है g x ईटा, तो डजंट इट विल मेक नो डिफरेंस बेसिकली. सो w ईटा g ईटा x d ईटा. Now replace the values from here. This is for 0 to x. For 0 to x, this is our function, so I can replace it here. And for x to l, this is our function, so I can replace it here. All right. So 0 to x. So what is gx eta? Gx eta is l minus x. So we broke it like this: w eta d eta plus x to l, and from x to l, this is our function. Our function is l minus eta x by tl, and w eta d eta. All right, this is what we get. So now by differentiating, I can bring it inside. Here you see the limits are also the function of x. All right, and I'm taking the derivative. So what happens is we take the derivative inside, but then we subtract the value of this whole function at x and then at 0. All right, so I have to use that theorem. So I will bring this inside 0 to x, and this will become the partial derivative because inside the function is of x and eta. Since inside function is a function of L, x and eta, that's why I wrote partial derivative. So I brought in, but then I need to subtract the value of this whole function inside function at eta is equal to x, upper limit, and then we need to differentiate this upper limit as well. All right, minus the value of this whole thing, at eta is equal to 0, but then I need to differentiate this 0, and that will make it 0, so I don't have to write it. The lower limit will just make everything 0, so you don't really need to write it. And then from the second one, second was from x to L. We are again getting the same thing inside because I can bring the integral in. This is w of eta and d eta, and plus I need to take the value of this inside function at eta is equal to L, but the derivative of L will make it 0. This is similar to here. It was a derivative of 0. I could have made it 0, but I have written it down, so let's keep it there. So TL w eta at eta is equal to x, and then the derivative of x. All right, this is what you got. So now this is 0. This whole thing is gone because of this thing, because this is equal to 0. All right, so all I get the contributions from here. So if I simplify, so if you take the derivative and simplify it, you are getting from 0 to x So you are getting from 0 to x, the derivative of L minus x, every other thing is constant for x, it's minus 1. So this you are getting negative eta by TL w eta d eta. All right, and from here, if I replace eta with x, this will give you L minus eta, eta by TL. So you are getting plus L minus eta, eta by TL, W eta. And from here, you are getting from x to L. And if you are taking the derivative with respect to x, it will give you L minus eta times 1 by TL and W eta d eta. And plus, minus this one. This is L minus eta, and eta is replaced by x, So eta and x are the same, so you can either replace x by eta or eta by x. It's the same thing, right? So here I replaced eta by x, so this was x, and here I'm replacing eta by x again, so L minus x, x by TL, W eta. So see, these are the same things and they cancel out. And all you are left with this one. All right? So this is our first derivative. So you got dy by dx equal to 0 to x minus eta by TL W eta d eta plus x to L minus eta by TL W eta d eta. So this is what you got from the previous slide. And now again we need to differentiate it again because I need to find the second derivative. Again differentiate with respect to x. So this gives you d2y by dx square is equal to, again if you bring that inside, again if you differentiate, you can bring this x inside, partial by partial x of this whole thing. Right? This whole thing inside plus the value of the function, and this minus will make it minus eta TL W eta at eta is equal to x, and the derivative of x is 1, and the other contribution is 0 because the second limit is constant, it's 0. And plus again x to L, I can bring the derivative inside. I'm using the same formula which I have used previously. This is, and now plus at L it's 0 because I need to take the value at L, and then the derivative of L is 0, so that will make it 0, minus the contribution will come from the lower limit. So this will be eta at eta is equal to x and the derivative of x. So contribution from the constants will be 0, constant limits will be 0. Here you see this integral 0 to x, this is 0 d eta because partial derivative, there is no x inside, so derivative with respect to x is 0, minus if you replaced eta by x, you will get x by TL Wx, right? And here it's again from x to L, it's again 0 d eta, and this will become minus at eta is equal to x, this will become L minus x TL Wx. This is what you got. So these are 0. Of course, this is equal to 0. This is equal to 0. Definite integral of 0 is 0. You are left with only these two things. So Wx by TL is common here. So you can add x and L minus x. You can add them up. So you got minus x by TL Wx and minus L minus x by TL Wx. So x plus L minus x is just L. Alright, so you got minus x plus L minus x by TL Wx. So this is nothing but minus L by TL Wx. So that is minus 1 over Twx. So this is your second derivative, d2y by dx squared. So if I bring this t on the left hand side, so therefore t d2y by dx square is equal to minus wx. So see, this is your solution. This was your equation. right? This is your equation 2, right? So this implies that y is equal to 0 to L w eta, and Green's function x eta d eta is the solution of equation 2. Right, so this is the solution of this equation basically. Alright, so we have proved it. Alright, so this is a proof. But where did this come from? So where did this come from? We have, when Green's function was given, I have proved that this is the solution, right? It's very easy. By differentiating our function twice, by differentiating our integral twice, this integral twice, and using this Green's function, I was able to prove that this is actually the solution of the given differential equation, right? But in the last slide, if you see, we had this expression that 0 to L w eta d2 by dx square of t g x eta d eta should be equal to minus wx. All right, and we said if this is equal to negative of delta x minus eta or eta minus x, this will exactly give you this thing. All right, so this is possible only if so this is possible only if d2 by dx square t g x eta is equal to minus delta x minus eta. So this is basically this is the basis of the Green's function. If t is constant, you can bring this outside. All right, if t is a constant, tension is constant, you can write it outside. All right, so basically you see this equation is the same as t d2 by dx square of y basically is equal to minus wx. So what we do is, if we are solving a differential equation, we can use the same operator. The left hand side is the same, you see, only y is replaced by g. But the right hand side, if you have any function of the right hand side, replace it with the delta function. Alright, so if you replace the right hand side with this delta function, the solution gives you the Green's function basically. That's how we get the Green's function. Alright, but in this problem which we just did, the Green's function was known to us. We developed the Green's function basically in one dimension, and we used that to find the solution. But here, if a differential equation is given, you can replace your unknown variable by g, and you can replace the right hand side by delta. Alright, so this gives you the Green's function. If you solve this, this is a Green's function. Alright, solution is simple, solution is not difficult. So this is what we got at the end. Here, as I just stated, that if this is equal to your delta function, then this property holds, so it will satisfy your differential equation. Or we explicitly proved as well, our Green's function was known to us, so we basically explicitly showed that this integral equation is basically the solution of this differential equation. Alright, so with this we stop today. What we did today is Green's function, properties of Dirac delta function, and development of Green's function in one dimension. So we actually developed Green's function in one dimension, and basically we considered a problem from mechanics, concentrated and distributed loads on a string. And we took the solution of concentrated load, and we approximated the solution of distributed load from that concentrated load with the help of Green's function. Alright, so this was the main basic idea of Green's function. We will continue with the Green's function in our next lecture. Till then, मुझे इजाज़त दीजिए. Allah Hafiz and Assalamu Alaikum.